Let's see more examples of channels. Okay. One example is what is called Pauli channels. Of course, it arises from Pauli matrices. We know this Pauli matrices, sigma 0. This is a Y defined. Okay, you can usually, it's also called, this is of course identity X, Y, Z. We called it sigma Z. You can call it whichever way you want. This is 0, 1, 1. Just flip the, it sends one basis E1 to E2, E2 to E1, 0 to 1, 1 to 0. And sigma Y is 0. I think minus I here, I don't know. Doesn't matter, I believe. Okay, this one. And sigma Z equal to, this is usually called Z, it is 0 minus 1. You can see that with respect to the trace inner product, this forms an orthonormal basis for M2C. This is an M2C, of course, that's clear. M2C, it forms a basis also. Okay. So then you define rho Pauli limit from P of rho equal to P0 times rho plus summation X, Y, Z. So is that P I mean, maybe I'll just write it. It is just 4 terms. Okay. It's just the conjugation by these things, of course. That's all. Px, sigma x, rho, sigma x. These are all self-adjoint, so you don't need to take star. And py, sigma y, rho, py, plus pz, sigma z, rho, sigma z. Okay. Of course, these are all the Krauss operators are this itself. These are Krauss operators itself. So this is clearly CP map. And since trace of, I mean, these are all unitary, self-adjoint unitary. If you take the trace, that will go. It's just only trace of rho is 1. So if it will just only, I mean, summation P, I mean, whatever, P0 plus Px plus Py plus Pz equal to 1. They are numbers. They are numbers. P0. I should have used Pi, P1, sigma 1, sigma 2. That will be easier to write the summation. Maybe next time I will write it. Pz are numbers in 0, 1 with such that they add up to 1. This is just a probability distribution. You have a probability distribution such that this happens. This is what is called a Pauli channel given by this probability density. That it takes with probability those state. Okay. So of course they are a CP map and it's a channel, it's a quantum channel. That's yeah. This is probability distribution which add up to 1. Then you have this Pauli channel, and this is of course CP, and it preserves the trace. Okay, those things are clear. Okay. So the one example is what is called dephasing channel. Is phases out channel. It is just when the P0 equal to 1 minus P and P Z equal to P, and of course Px equal to 0 equal to Py. Okay. Okay. We just take in this equation. Then what does it become? I mean, if rho is some rho is a state, so it will have determinant equal to 1. So it will be lambda 1 minus lambda and some alpha bar, such that we know that condition also, such that I mean, you can actually we wrote it like x. I mean, 1 plus x, 1 minus x, we had half. That's how we represented in the beginning. You can write it this way also. You can, here, I mean, we are not using that property, but I'm just writing it like that. Okay. Then this, for corresponding to this P of rho is just equal to, if you just compute it, it will, I mean, this is just 1 minus P. I mean, this is going to be just 1 minus P times identity. I mean, 1 minus P times rho. Rho will go to 1 minus P times rho. Then P times sigma Z, no? Sigma Z. Sigma Z, rho, sigma Z. Okay. Sigma Z is diagonal. So it will just multiply. I mean, when you conjugate, it will multiply both sides by the diagonal element. And this will just become, this will be just lambda, and this will become 0, 0, 1 minus lambda. We just, the reason is, if you multiply by this, you will get 1 minus P here, and 1 minus P here. But when you multiply by this sigma Z, that has two entry, 1 and minus 1. This is identity, 1 and minus 1. It will multiply by 1 here, minus 1 here, 1 by minus here. So this will become minus. When you add those two things, that will cancel. So this takes a quantum state to a classical state. It removes the, I mean, it dephases it. Okay? This is the phase between those two things. It dephases. That's why it's called dephasing channel. Okay? It takes any rho to a classical channel. It becomes a classical channel. Of course, this is, they add up to 1. So this is a diagonal, which is classical. Okay. And we know the, so there is something called depolarizing channel. These are just examples, not much to, I mean, very easy concepts. Conceptually, they are easy. Here we take P0 equal to P or 1 by P, 1 minus P maybe. Okay. And Px equal to Py equal to Pz equal to, no, I take P equal to P by 3. Yeah, P equal to P, 1 minus P. Okay, 1 minus P is fine. This is equal to P by 3. Okay. Then it is just rho will go to 1 minus P times rho plus whatever, sigma, I mean, summation of those things divided by P by 3. P by 3 you will get. Okay. And you have this equation. For this Pauli channel, you have this equation. That is, if you have for any operator, this is true. Any rho plus sigma x rho sigma x plus sigma y rho sigma y plus sigma z rho sigma z divided by 4, 1 by 4, or you don't need that, which is equal to trace rho times identity. This is identity matrix, identity times divided by 2. Okay. You have this equation. I mean, this is clear. This follows, because if you have any group, you are just, I mean, even if you have any group, you have an automorphism or something. Then if you have the alpha G of rho, something, summation over G. Okay. If you use fix a G and if you apply them, I mean, maybe alpha G is conjugation or something. UG rho UG star. You have anything. Okay. Then if you have a fixed UG naught and UG naught star, okay, it will just go here and the summation will be same. Okay, so this is equal to the same summation. Okay. Same summation, that's what you will get. So this commutes with all this. I mean, this commutes with this commutes with all UG naught. But in this case, all this unitary sigma x, they generate. If it commutes with all this sigma x, that's an orthonormal basis. By linearity, it will commute with everything in M2. So it will be a scalar. So it has to be a scalar. So it is scalar times identity. Okay, and that scalar has to be trace rho, because trace has to be, I mean, the trace has to be preserved on both sides. So trace of this is trace rho. This is also trace rho, because you can bring sigma x here, and this is also trace rho, and this is 4 times trace. So Yeah, four times trace. So that is trace row. How am I getting two? Well, I have to get two somewhere. Mm. Hmm? Trace of sigma is no. There is no trace of sigma. Or conjugating or bringing it here, that will become one. Okay, so it is just trace row. So yeah, it is just trace row one. Maybe I mean I need this two because this is a state. 1/2 is a state. This is the what is called maximal mixed state. Okay, this is the, I mean, when I define what is called quantum coin tossing, this is the most fair quantum coin tossing. It has, with half probability, it takes head and tail in the quantum toss. Okay, so this is what is called maximal mixed. This is a mixed state. It's not a pure state. Mixed state, and identity by two is this is a maximal mixed state. Okay, so I should get maybe there is no. Okay. There is maybe 1/2 only. 1/2 only. 1/2 or 1/4? I mean, 1 by? No, no. This is four times trace row. So if you divide it by 1/4, 1/4, oh yeah, you don't get anything. 1 by, there is, mm, no, it should be 1 by d square. See, in general, for a general, this row w x y star, okay, summation over x and y, and 1 by d square. Okay, there are d square of them, so that is this, and that will commute with that, and there will be d square summation, though that will cancel. So yeah, it will be just identity, right? Trace row of uh, trace row is one. Trace identity. I mean this. I mean this is because trace of identity is two. Okay, that's why. So that's why I have I by two. Yeah. I mean, I have having in mind that trace of identity is one, but trace of identity is two here. We are using capital trace. Okay, that's why. So this is fine. Okay. So, so we have this equation. Okay. And our row is this. Our channel is this. Of row is uh, small p, p of 1 minus p, right? 1 minus p times rho plus p by 3 into then sigma x rho sigma x plus whatever. We have that. So we have this summation is equal to 4 times whatever. So if you it's just addition and I mean, taking to the other side and the other thing, this will imply that I remember this. This is just 1 minus 4 by 3 p times rho plus 4 by 3 p times identity by 2. So this is the map, actual map. Okay, I mean a priori it's not clear it's CP, but we have defined it through the behind it defined it through the Pauli channel. So it is a CP map. Okay, and we have this, and this just gives that with probability 4 p by 3, it gives this mixed state, and with the remaining probability it has this. Of course, p should be less than 3 by 4. Okay. Then I mean that's what this channel does. Okay. It takes a row and it mixes with some this maximally mixed state with probability 4 by 3p. Okay, that's all. Okay, now we can have a generalized Pauli channel. As I just wrote it with W's, it is basically that. Generalized Pauli channel, or you can call it Weil channel. Okay, we have seen Weil operators, W, X, Y. So on CD, we have this W, X, Y, unitaries, okay, unitaries of CD. They are unitary operators. We have already defined these Weil operators. Okay. So then the generalized Pauli channel is this. I mean, when of course x equal to 0, y equal to 0, that is it is identity. So xy equal to 0 to d minus 1. Okay. D minus 1 w xy rho w xy. When of course d equal to 2, this gives Pauli matrices. Okay. So it is this channel, and so I forgot to bring the paper again. Okay. So of course the Krauss operators are clear. It's clearly, I mean, these are, I'm sorry, we need a pxy here. This has nothing. This will just scalar times something, right? I mean, if you have it, this is just scalar times identity. There is nothing. There's nothing in the channel. Okay. I need a pxy where pxy are in 0, 1, and summation pxy equal to 1, where xy runs over 0 to d minus 1. Okay. So this is a channel. Okay. Okay. So we know that these things, wxy with xy ranging, I mean, in 0 to d minus 1. Okay. This is an orthonormal basis for MDC with trace inner product. With trace inner product. Okay. Okay. Now you have this gamma, you know, the summation I tensor I. Okay. Summation I tensor I for that in CD tensor contained in CD tensor CD. Okay. If you take this WXY tensor 1 acting on gamma. Okay. So notice that this inner product with another WXY, WX prime Y prime tensor 1 of the same gamma. Okay. If you take this inner product, you can bring it here. You will get WX prime Y prime. And you know this, we have this formula, right? I mean, or you can take it that side. We have this formula that we have already used this gamma, some x tensor 1 gamma is equal to trace of x. You just direct computation will lead to it. I mean, gamma looks like this. Then if you have gamma and gamma here, x tensor 1, this 1 will give ei, ej, and that will be only when I equal to j, it will be non-zero. And if you do the summation, you will get trace x. Okay, this formula we have used. So if you take it here, you will get wxy, this star, this, and you will get basically trace of this star that. That is, I mean, that is equal to, that is delta xy basically. I mean, delta x prime, y prime. Okay. So only when xy is equal to x prime, y prime, that is non-zero. Otherwise, it's 0. So these things imply that, let me write here. This W of xy tensor 1 acting on this gamma. Okay. This with xy equal to 0 to d minus 1. Okay. Contained in CD tensor CD is an orthonormal basis. Okay. From whatever we have seen, this is an orthonormal basis. Okay. Okay. So why are we doing this? I mean, I want to compute the Chai matrix of this. Chai matrix of this channel. Okay. So the Chai matrix of this channel is P of this channel rho. That's what I want to compute. That is equal to Okay, let me call this by some name. I mean, these are what are called maximal, this will be some, I mean, this is a maximally entangled state. If you apply this, you will still get maximally entangled state, and you will get a maximal, I mean, you will get a set of maximally entangled state as orthonormal basis for this. Okay. Okay. Now, if you, so now I want to compute this one tensor rho acting on this, right? This is the chi matrix, right? Okay. So this will be basically, I mean, this is just on one thing it will act as identity, the other one it acts like W conjugation by WXY, right? So it will conjugation by WXY, there will be a WXY here, there will be a WXY here. There will be one tensor WXY here, one tensor W. I mean, this is basically conjugation by, I mean, rho is basically conjugation by WXY, and you sum it. One tensor rho is one tensor WXY, conjugation by that. So you will get a one tensor WXY here, you will get a one tensor WXY here. I have used WXY here, maybe you can put the WXY here, both are same, okay? I mean, you will get a transpose or something, doesn't matter. You can put the WXY here, okay? Okay. So maybe one tensor. I mean, our convention is to take identity here and then go here, okay? So this will be basically summation Pxy, okay? Did I call that by something? Oh, this is equal to, let's call it phi xy. Okay? I'm using phi here. Okay, that's okay. I haven't used. Okay, Pxy, P. That is not phi xy, Pxy. This is what you get. Notice that Pxy is an orthonormal basis. So summation Pxy equal to 1, because that's an orthonormal basis. So if you take this state, if you add it, it will be identity in D. Okay, but you are taking a probability distribution here, you get something like this. This is what is called Bell diagonal state. This Bell diagonal state is the chi matrix of this generalized Pauli channel. Okay. So that's what we have computed. This is clear, I believe. Okay. We just apply the definition, you get this. Okay. So there are more examples of channel. We'll see in the next class. Before that, I want to talk about what is called Petz recovery map. This Petz is a quantum probabilist. Petz recovery map. Who defined this recovery map? So if we have a n from L of HA to L of HB, a quantum channel, then of course we have n dagger or n star from L of HB to L of HA. Okay, and let some sigma be in L of HA, the state. Okay, then you define the Petz recovery map, which I'm again denoted by script P of this n corresponding to the sigma acting on any x is equal to, first I'll come to this, I will define this, what it means. This may not be invertible, but I will tell you what is this. x n of sigma power minus half. Okay, I do this. Then I apply sigma power half here, sigma power half. This is what is called Petz recovery map for x in L of HB. Sorry, this should be, I forgot something. Sorry. N star of this, n star of this, then sigma power half. I take x and conjugate with n sigma power minus half, n sigma power minus half. They are positive operators, but I have to define what is this inverse. Then I apply n star. Okay, x is in L of HB. Okay, this is also in L of HB. So you have this map, which is in L of HB. I apply n star, you get it to L of HA. Then I apply sigma power half on both sides. So what this inverse is, this n sigma is a positive, it's positive operator, positive matrix. So by spectral theorem, it will have, it may have kernel, it will have positive eigenvalues. So invert only those positive eigenvalues. So invert it on the support projection. Where it is zero, you may make it zero. You call it zero. That's all. Okay. So that is what this n sigma is. Inverse on the support of n sigma power half. Okay. You can take the square root. Okay, it is just the square root of the eigenvalues. You can take, and then take lambda power minus half on the support. Okay. So it may not be, it's not a inverse on the whole of it. Only on the support, it's an inverse. Okay. So then you apply these things. So this is what is called Petz recovery map. Why is it called Petz recovery map? We will see. Okay. So this is not a trace preserving map, but this is a trace non-increasing map. Okay. It will not increase the trace. It will be. So they are all very easy, but let me make it a proposition. N, it's rho, right? P N sigma is, of course, it is CP is clear. I don't have to write it because you are conjugating with something which is CP. Then your star is CP, and then you are conjugating with sigma. That's also the CP map. So CP is unital CP. Because n is trace preserving, n star is, no, this is not unital, sorry. I mean, n star is unital, but this may not be unital, is CP and non-trace increase. It doesn't increase the trace, okay, less than or equal to. So we have to only prove trace non-increasing, okay. So we have to compute the trace of P of n sigma of some x. Okay. We have to compute this. Okay. That is equal to trace of, let's write the definition, sigma of then n star n sigma power minus half, okay, x n sigma power minus half, then sigma power half. Okay. By definition of the star is with respect to trace inner product. Okay. So you can put the n here and you can remove this. So this is equal to trace of, no, I bring it, sorry, first I bring it, this is equal to, I can bring this sigma power half here. Okay, make it sigma like this. Then I apply this. Then trace of n of sigma, okay, times n of sigma power minus half, okay, x n of sigma power minus half. Okay. Huh? Sigma power minus half. Sigma power half. Last one is sigma power half. Sigma power half, sigma power half. Initially inside the n star, you are conjugating n sigma power minus half. Outside you are conjugating sigma power half. It is just, well, I mean, it's not unitary conjugation. It's yeah, it's conjugation. A star kind of thing. X going to AX A star. Here A star equal to A. So that's a that kind of conjugation. Hmm. Add map. Add. Okay. Conjugation not the right way. Add map. Add. This map. Huh? Huh? Yeah, it's not inverse. It is star. Okay. Yeah, it's not inverse. It's star. Yeah, that's clear. But that is not CP map. Okay. If you conjugate with inverse, that is not CP map. That will be homomorphism, but it will not be CP map. Only X going to AX A star, this is a CP map. Okay, this preserves positivity and CP map. If you have A inverse, it will not be. Okay. Okay. So we have this. Now you can bring this n sigma here. So this is just trace of n sigma power half, n sigma power half, minus half. Okay. This will not be equal to 1, but this will be the support projection, basically, right? I mean, this is n sigma, which is 0 on the orthogonal complement of the support of n sigma. And it is basic, this is also 0 on the orthogonal complement of support. And there they cancel each other. So it is just that support projection you will get, where P is the support of n sigma. N sigma is fine. N sigma for they have the same support. Okay, times x. Here to here. This is the trace inner product, no? The trace inner product says that, yeah. So n will come as here. This is the inner, I mean, you need star for inner product, you need star, that doesn't matter. You can keep it like that. This is like inner product of this with this. So you bring the star here. I mean, that will become n. Okay, times this. Okay, and if you want, you can take the P support here, and this is less than or equal to trace of S. Is clear, no? I mean, this is, you can bring the P here if you want. You can, if this is a projection, you can bring one of the P here, and that is less than or equal to 1. So, I mean, that is less than or equal to X, so trace will also be less than or equal to. Okay, so this is clear. So it is trace non-increasing. Okay, okay. Now, one thing is clear. If you have sigma, if you apply P n sigma of sigma, you will get sigma back. I'm sorry, n P sigma of n sigma, you get sigma. I mean, if n sigma is invertible, okay, this I will not prove, I will orally say that, then P n sigma of n sigma is sigma. It recovers a sigma, right? If you put n sigma here, if it is invertible, then this becomes 1. Okay, n star of 1, n star is unital. N star is unital, right? N is trace preserving, so n star is unital. We have proved it. So n star of 1 is 1. I mean, if x is n sigma, this becomes 1. N star of 1 is 1. So you get only sigma here. I mean, sigma power half sigma, we will give sigma. I mean, I'm computing for P and sigma. P and sigma of n sigma is sigma, when sigma is invertible. If it is not invertible also, it is sigma. That's what you want to prove. Equal to sigma for all sigma in L of H, sigma state on HA. Proof. Okay. First, let us do the computation. So P of n sigma of n sigma. Okay. I mean, this n is, I'm using capital letter, script both are okay. So P of n sigma, which is equal to, we have the sigma power half n star of n sigma power minus half n sigma power minus half. So this is, this is equal to sigma power half n of that support projection. Support projection times sigma power half. Okay. So notice that this is a positive operator, this is a positive. If x is less than or equal to y, then a star is less than or equal to a star. You can just bring it here, and this is a, you can bring it. The positivity. We didn't go through all that. In this course, but you have gone through in a different course. X is greater than y means y is greater than x means y minus x is positive. So if you take this will be a y minus x. So if you have any positive operator in the middle, then ax a star. This is also positive. So because of that, this is less than or equal to identity. So but n star is Cp, okay, and this Tp will preserve this partial order. Okay, so this will imply sigma power half n star of identity times sigma power half. So this is less than or equal to, this is 1. N star is unital, so this is 1. So it is just sigma. Okay, so this is less than or equal to this. We want to prove it's equal to that. Okay, this is less than or equal to that. So we have n p n sigma of n of sigma, okay, is less than or equal to sigma. Okay. So that means this minus this is greater than or equal to 0. Trace is a faithful state. Trace of an operator, trace of a positive operator is 0, then the operator is 0. Okay. So if you compute the trace of this, trace of P n sigma of n sigma, we have done the computation already there. I will show it here. We have already done the computation here. So if you take the trace of this, you get, but instead of x, I have n sigma here. So if we take n sigma here, this will be n star of all those things. Okay, this will be just basically trace of yeah, you will get n star of the wait a minute. You will get you have n sigma, so you will n star of that projection. Okay. No. I'm trying to. That should be equal to. No, sorry. I want to look here. Sorry. I don't want to look here. N star. I want to look here. Okay. Now trace of this n sigma power minus half x n sigma power minus half. So I have n sigma here. Okay. Now I have n sigma power half n sigma, and then another n sigma here. So yeah. So this will be equal to trace of n sigma. You will get, see, if you have n sigma here, you will get that projection onto the support times n sigma. But projection onto the support times n sigma is n sigma itself. Okay, right? It is just those eigenvalues, you can clearly see. Okay, so it is just, n sigma is also 0 outside the projection. So it is basically n sigma. So trace of n sigma is sigma. Okay. So if you, we have already done that computation. This is equal to trace of n sigma itself, which is equal to this is n sigma is trace preserving. So this is equal to trace of sigma. Okay. So this implies that these two have same trace. So trace of E of n sigma minus sigma is 0. And we have proved that this is, sorry, the other way. this is 0. Okay, and trace of some positive something is 0, so it has to be 0. So this implies P of n sigma of n sigma is equal to sigma. Okay, and both are same, whether plus or minus. But I want to use the fact that trace of positive operator is 0. Negative operator 0 is also 0. Okay. So this is a recovery operator for sigma, even when sigma is not invertible, and sigma is not invertible. Okay. So they are true. So now let us compute. I mean, so this is something. I mean, this is the recovery operator, Petz recovery operator defined for any CP map. Okay, and it's a computation you can do for any CP map. There are many definitions of CP map, and you can do it. We will do for some very easy thing, which is our partial trace, which is a CP map, of course. So for that, we will do the Petz recovery map computation. Okay. So for partial trace. Okay. So you have HA tensor HB. Okay. L of this to L of HA. This is the partial trace. Okay. Trace B. Okay. We have the partial trace, which is our CP map now. Okay. So you call it maybe N. N is CP map. Then you know what is N star. N star is a map from here to here. N star of any x is equal to x tensor 1, right? We have already done this. We have worked on this, right? If you write the, I mean, for us, the partial trace is defined through as a linear functional. Okay, partial trace B of any x AB, okay, times y times trace. This is a linear functional acting on any one tensor y, right? One tensor y tensor n. X tensor 1, I think, is equal to no, times x is equal to trace of xab times x tensor 1. Okay. This is how we define the partial trace. Just the definition will give you that x going to x tensor 1 is the adjoint. Okay. This is how we define. Then we compute it through the matrix units. Okay, and not orthonormal basis, matrix units or whatever. Okay. Okay. So this is the n star. Okay. Okay. Now we have a sigma in sigma AB in L of HA tensor HB. We want to compute the Petz recovery map for this. Okay. Okay. Then Petz recovery map. P for this n of some sigma of some x, okay, will be. So we will have x tensor 1, and I mean, we have a sigma AB, okay, and sigma A is equal to the partial trace B of sigma AB. Okay. That's our notation. Then we will get sigma A power minus half x sigma A power minus half tensor 1. If you apply the n star, this is what you will get. And sigma AB power half, sigma AB power half. This is what we get. Okay. Right? Okay. So this is what we get. I erase this. So this is identity on B. Okay. If J is an orthonormal basis for HB, some J is an orthonormal, I mean, this J from 0 to dB is an orthonormal basis for that, then this you can write it as sigma AB power half, okay, sigma A power half, sigma, I mean minus half, sigma minus half, sigma A, tensor this J, okay, then sigma AB power half, okay, or summation over J.
equal to 1 to dB minus 1.
I am just writing identity.
1B is equal to summation Jj, right? J equal to 1 to dB.
I'm just writing identity as Jj, summation of that, and that summation I'm taking. That's what I have. That's the only thing I have done. Okay. Now you can see that this, you can take sigma a power half j one side and sigma a power half, I mean, the another sigma j one side. Okay. And you will get a sigma ab power half on the other side. This is just to get the Krauss operator from here. Okay. From this equation, I conclude the following. I'm saying the following: sigma AB power half, okay, sigma A power minus half, then J. This J, we can just act on this J, sorry, tensor J. Okay. This J equal to 0 to dB minus 1. These are the Krauss operators for our partial trace. I mean, for the Petz recovery map. That's clear, no? You have to conjugate with this and sum it with J. That is what the Krauss operators is. So you are basically conjugating with respect to this. Okay? If you do this, then you get the Jj that side, and you get the sigma a power minus half on that side, and sigma, this is on the both the tensor. So you get this. So this is the Krauss operators, right? Okay. Once you know the Krauss operators, you can write the dilation, isometric dilation. Okay. I mean, it's just you have to keep the map as it is, as a one single matrix. That's all. Okay. So you can, I mean, there will be a complementary Hilbert space for the unitary dilation. That complementary Hilbert space will have the dimension of the number of Krauss operators, right? That will be the number of Krauss operators, right? So we have this HA tensor HB. This is our initial space. We have another HB. HB or HB prime, same as HB, okay? This, okay? So we want to get a V from here to HA tensor HB, tensor HB prime. Okay? That is nothing but summation sigma AB power half sigma A power half. I just write summation over J equal to 0 to dB. Let me write it and explain. Okay, dB minus 1. Okay, sigma AB tensor 1. Maybe I call it B prime. Okay, B prime is same as B. Okay, 1 B prime tensor sigma, and this should be half, sigma A power half tensor 1B tensor 1B. Okay, then sigma 1 A tensor J tensor J. Okay. This will be the isometry. See, if you have the Krauss operators, say Vi, okay, Vi from I ranging from 1 to D, then you just write it this V1 up to Vd, whatever. That will be the dilation. That will be the isometry. But instead, you can write it as, you can take that is just summation Vi, this I, right? In that space. Right? You will have one space for each Vi. It will be just that amplification. So it is basically that. Okay. So that is what I have done. So this is the isometry. But then this J tensor J is just the gamma. So this is just equal to, if you take the summation inside, this is just sigma AB power half tensor 1 B. Okay. Then sigma A power minus half, this is minus half, tensor 1B tensor 1B, at then 1 tensor gamma BB. This is the unitary dilation. Sorry, this is the isometric operator for the dilation. Stein-Spring isometry is this. Okay. So this is even for the partial trace. It looks like it's not very trivial. Okay. The recovery map is this. Recovery isometry map is this. Of course, you can look at the complement and other things using it. Okay, that's all about Petz recovery map. There are some exercises which you can do. Okay. Next, we want to see something new. It's called, we have already defined what is called a PPT state. Partial transpose, positive partial transpose state. PPT, partial transpose state. Okay, definition. We have already defined this. Rho in HA, tensor HB, a state. Okay. Then this is PPT, rho is PPT, positive partial transpose state, PPT state. If you take the TB of rho is positive. We have proved that it's equivalent to saying TA rho is also positive. TB is rho is positive if and only if TA rho is positive. Okay, we have proved that. Okay. So it doesn't matter with respect to which factor you are taking the partial trace. Okay. This is partial. So now we make this following definition. N is from HA tensor HB to HA prime tensor HB is completely PPT preserving. Okay. If you take TB here, partial trace, I mean, this is partial transpose, not partial trace. TB is partial transpose. I mean, if by mistake, if I say trace, it's not trace. If I use TR, that is trace, this is partial transpose. Okay. You take the partial transpose here, then apply N. Okay. Then apply the partial transpose there. Okay. This is CP. Okay. Of course, if that is a channel, this is a channel, it will all be trace preserving. Okay. That's not the problem. So it's only, I mean, partial transpose is also trace preserving. So it is only the positivity, complete CP map we have to worry about. Okay. So this is CP. Okay. Okay. Hmm. I am a bit confused. Okay, I'll come to that later. So this is about CP map. Okay, this is about, so I'm confused about something else. Anyway, we'll see it in the next class. So proposition N is CPPT preserving completely positive completely positive partial transpose state preserving, PPT state preserving, CPPT state preserving. Okay, which is the definition, which actually means that is what we want to say. Then N of rho is PPT for all PPT, rho PPT, for all PPT, positive partial transpose. If rho is PPT, then N of rho is also PPT. In a sense, if one tensor rho is PPT, then I know one tensor N also has the property. We'll see when we compute the Chai matrix, it will be clear. Okay. Okay. Proof of this. So rho is PPT, positive partial transpose preserving. I mean, okay. Is a PPT state. Okay. Then we want to talk about N of rho is also positive partial transpose. Okay. I mean, for that we need to have a definition. No, N is from L of HA tensor HB. I mean, it should cannot. I mean, there is no meaning if it is from HA to HB. It has to from HA tensor HB to HA prime tensor HA prime. So for that only only for a bipartite state this makes sense. Okay. So if it is partially, if it is PPT state, you can take transpose with respect to one of them, and that is positive. Okay. Rho is PPT state. Okay. Then we want to prove T B prime of N of rho is positive. That's what we want to prove. We want to prove this is greater than or equal to 0. Okay. But then T B prime N of rho, I mean, TB is a map. Okay. TB of N of rho. Okay. We can take this. Okay. I mean, TB is a operator map, something called super operator. Okay. So TB prime of N. Now I apply TB. So TB is 1. Partial transpose, if we take it twice, it's 1. So now this is CP. TB rho is positive, is greater than or equal to 0. This is positive since TB of rho is positive, and TB prime N TB is CP. Okay. Okay. That is CP, and that's the definition. So it's clear. Okay. Okay. So this is more N from HA tensor HB to HA prime tensor HB prime is CPPT preserving state. You see, completely PPT state preserving. Okay. If and only if the corresponding Chai matrix of N is a PPT state. That's all, as expected. So proof. We just compute the Chai matrix, show that it is some sort of partial trace. I mean, what does it mean by PPT state? Chai matrix, so I have to explain something, sorry. Chai matrix is, that is, if phi is a Chai matrix is, it is in AB, A prime, B prime, right? Chai matrix is in HA. This is the initial one, HB. Okay. Tensor HA prime, tensor HB prime, right? Chai PPT state with respect to B prime. Okay. See, you have to take the transpose only with respect to B. Yeah. AB prime B. Okay. You have this 4 tensor. You are taking the transpose with respect to this and this, which you can do. TB tensor TB prime. 1 tensor TB tensor, 1 tensor TB prime, you can just apply. And TB is just that summation. I mean, you have that matrix unit. You are just conjugating with the matrix unit and you get that. Okay, I mean the flipped one. Okay? If it is IJ, you will use JA and get that. Okay, so you do this only on these 2 entries. Okay, It is with respect to that is a PPT state. Okay, when A and A prime is fixed, with respect to the BB prime factor. Okay. Okay. So what is the Chai matrix? This is just one tensor n, okay, acting on this, right? Gamma. This gamma is on the big one. See, we have this gamma of A, B, A prime, B prime. Okay. This is on 4 product. Okay. So now you have something for this and you have something for this. It is just a tensor of those two things. Okay. So, okay. Now this Chai matrix is nothing but is equal to n of the one tensor n, which is acting on HA tensor HB, okay, and it lands in HA prime tensor HB prime, acting on phi of this gamma, okay, and I mean you have to divide it by the dimension of this one, some constant, okay, so that it becomes a state. You have to divide it by the dimension of this whole thing. Okay. No, 1 by d, I believe. By d. Okay. EIJ tensor EIJ kind of thing. Okay. So, okay, the point is this. Now you are applying one tensor n on this. Okay. Okay, I will go there. You are applying one tensor n acting on this gamma. I mean, you have to divide it by a constant for a state, but let us just compute this. Okay, not one tensor this. I want to apply. I want to use the transpose map also, partial transpose. One tensor T B prime n T B. Okay, I mean some n is completely positive PPT preserving map if this is CP. Okay, and some map is CP if and only if the Chai matrix is positive. We have proved that. Okay, so I am taking one tensor this acting on this gamma, okay, where gamma is in the 4 tensor product. Okay, okay. Now this is equal to, of course, one tensor of TB prime, okay, n, and this TB of this, whatever, gamma. Okay. Now notice that TB of gamma, okay. See, I mean, this TB, there's a small problem. We have, not small problem, notational problem. We have this HA tensor HB. This Chai matrix is in this HA prime tensor HB prime. The Chai matrix, I mean, there is no confusion, but it is just the notational confusion. This is on this. This gamma, I mean, did I write gamma in that? Gamma is, P is in that. Gamma is in HA tensor HB. Again, this is also HA tensor HB only, right? Of course, this is a maximally entangled state. This is how it is. Gamma is that II. I mean, the orthogonal matrix here tensor this. That is how gamma is. Okay. So here you are having TB. You are having TB. This is prime. Okay. This is the range. Okay. B prime is different. There's nothing to do with B. Okay. So you are initially applying this TB on this. Okay. You are applying TB on this. Okay. But when you have gamma, if you apply TB here, it is same thing as applying TB here. The reason is gamma is a summation of something. Okay, it's a, let me not. Gamma is going to be, if in general, the gamma is going to be, it is just I
tensor J, tensor, again the same I tensor J, right?
It's not that. Gamma is this. Okay. Gamma is going to be two different things. So usually gamma is what? Usually for two product, gamma is going to be I tensor I. Okay. Gamma. This is going to be Ij tensor Ij, right? Some summation, of course. Summation over I, summation over Ij. Okay. So here we will have something like this. We will have something like this. Okay. This is a summation. Gamma is summation of these things. Okay. Now, if you apply this partial transpose on this, okay, HA tensor HB, HA tensor HB, you apply the partial transpose as this. In this summation, J will become J and I will be flipped here for this. J and I will be flipped. That's what the summation is. I mean, you not in this I. This HB will have an index. Let me explain it here for two index. This gamma, maybe with Eij, tensor Eij. This is how gamma, right? When you have two product, gamma. If you apply the transpose here, this will become Eji. Eij tensor Eji. That is same as, since you have a summation, Eji tensor Eij, right? This TB, the partial transpose on the second one, is going to be Eji. It will become Eij, will become Eji. No, this is both B and B. They are same. Both are same. HA tensor HA. That is, this maximally entangled state is defined only for when both are same. Here, I mean, here there are two products. That is why the confusion. That's why I'm explaining for one product. Okay, only one product. Okay, when you have one product, gamma, this is HA tensor HA. I mean, this is a state on HA tensor HA. Okay, gamma is a vector in HA tensor HA. Okay, this is a state on this. This is that Eij tensor Eij. Okay, if you take the partial transpose, this will become Eji. Okay, but this summation Eij tensor Eji. That is same thing as summation Eji tensor Eij, because it's a summation. Okay, you can flip on the other side. So instead of taking the TB on this, it's same as taking TB, I mean TA, whatever, TA on this, transpose on this. So that is what I'm saying. If you take the transpose on this, you are taking the transpose on this. It is same thing as taking the transpose here. If I write the whole thing, it will be messy, but it's clear, I think, from this example. If you take the transpose here, initial transpose, these are all same space. It is like taking the transpose here. Okay, so you can take the transpose here, but then that is identity here. It will just come out. Okay, so if you just look at that carefully, this thing is same as TB tensor TB prime. Okay, then there is this one tensor eta. Okay, then this whatever that gamma, big gamma AB tensor. I mean AB A prime B. I mean that big tensor gamma AB. Okay, so we have got this. Okay, now this is TB tensor TB, and there is of course one everywhere else. One tensor this, one tensor this, one A tensor this, one A prime tensor this. So this is basically taking partial transpose with respect to B and B prime. Okay, so this map is CP if and only if this partial transpose with respect to B and B prime is positive. That is precisely what that thing says. Okay, this is a PPT state if and only if, sorry, I am saying that it's there. It is this is a CPPT state, CPPT map, okay, completely PPT preserving map. If and only if this is the one, no? PPT map. No, it's here, sorry. PPT map, if and only if the Chai matrix is PPT. Okay, with respect to taking partial transpose with respect to B and B prime. That's what precisely it has said. There is nothing in this proof except that you can use this. You can take this TB, if you apply TB in this, you can take, I mean, if you apply transpose here, partial transpose here, It's same as saying partial transpose in this. Okay, that's all. To take transpose here is same as taking transpose here. So that's what we are doing. You want to take transpose here, that is same as taking the transpose here. Okay, but because its identity here, it will come out and it will become like this. That's what you have. Okay, so I'll stop here.